All right, so the next part of this module is circular motion, and we're going to learn about what kind of objects are in circular motion. So a Ferris wheel is in circular motion. The Gravitron, if you've ever been to the state fair, hopefully you've got to experience the Gravitron. It's a circular spaceship looking ride, and it goes really, really fast, and your feet start to come off the ground and you start to move up the walls, so it's really cool. Hopefully you know what that is. And then also a carousel is in circular motion, right? And so one thing I want to tell you about objects that are in circular motion, obviously they follow the path of a circle, which both of these objects do. So if you can tell, object number one is kind of on the inside here, and object number two is on the outside. Well, the thing about objects that are in circular motion next to each other like that, object number two is actually traveling faster than object number one. And the reason that is because their time is the same, but this object number two has a larger circumference to cover than object number one. So if you kind of watch things like horse racing or car racing, or even just people racing, you'll notice that they want to get in the inside lane, right? The lane closest to the middle. And the reason they do that is because that diameter is a little smaller, that arc length that that object has to make. And so it doesn't require as much speed as the car on the outside that's farther away from the middle. They actually have to go faster to keep up with the cars on the middle. And so it's got to do with that arc length and how fast that object can move around that arc length. So just thought you might find that interesting. Okay, so we're going to look at a few things about an object in motion, right? And so what is the speed of an object in motion? So first of all, the time, right? We're familiar with speed and velocity being distance over time, but for an object in circular motion, time is the amount it takes to make one revolution, okay? So around the circle. So the time it takes to take one circumference, basically. That's what the time is going to be for an object in motion. And we call that the period. So we're going to work on finding the velocity formula. We're going to work on finding the acceleration formula. And then lastly, we're going to go ahead and look at the force formula for an object in circular motion. We haven't touched on forces yet. That's going to come up in the next module or so, but we're just going to introduce forces here. All right, so let's look at the speed of an object in motion, okay? So in order to find the time that it takes one revolution, right? The period is the time it takes to make one revolution. Well, we know circumference formula is 2 pi r. And that circumference for an object in circular motion is going to be the displacement, okay? While you know, the speed velocity vector may stay the same length and magnitude, a velocity vector is always changing angle because of this circumference. So we know velocity is distance over time. Okay, so in this case, the circumference is our distance and the t is our period. So if you notice, it's capitalized because for an object in circular motion, it goes around the circle in a certain period of time, and we call that the period. So we can derive acceleration from this, right? So we know acceleration is velocity squared, for an object in circular motion, it's velocity squared over radius. Now, it's very complicated trigonometry based for me to derive this formula for you of how we went from velocity 2 pi r over period to acceleration velocity squared over r. And because this course is not trigonometry based, I'm not going to break that down for you, and I'm just going to go ahead and give you the formula. We can also write the formula this way. So the acceleration of an object in circular motion could be v squared over r, or it could be 4 pi squared r over t squared. Okay, So again, I'm not going to derive those two for you because it's very trigonometry heavy. And so I'm just going to give them to you. So make sure that you write these down, okay? All right, so what causes centripetal acceleration? Well, that's a centripetal force. So we have to have a force acting on our object, okay? Remember, forces cause acceleration. And again, we'll get into that a little more in the next few modules. But for now, we're going to go ahead and when we want to figure out what the centripetal force is, we're going to use 4 pi squared r over t squared. That's our acceleration times the mass of the object. Remember, we know a force is mass times acceleration. Okay, so that 4 pi squared r over t squared is our acceleration, and then times the mass. So the m is going to be the mass in this case. Just to let you know, we also have a saying in physics or physical science that there's no F word. So there is no such thing as a centrifugal force. That is not a physics term. That is a term that people like to use to talk about when the outward pull on an object, but that's actually not a real force. It's only a centripetal force is what keeps something in motion. And that opposing force is not a force at all. It's actually inertia. So, you know, when you're driving in the car and somebody makes a real fast turn and you hit the door because you weren't, you know, prepared for it, that's not a centrifugal force that's causing you to fly outwards. It's actually your inertia. So just know that there's no such thing as a centrifugal force. And that's why we say there's no F words in physics. All right, so I was talking a little bit about the vector diagram of an object in circular motion. And so, again, you can see all my arrows are the same, but you can tell the angles are changing, right? And if you look at it, it's kind of pointing north, south, east, and west. That's just an example of how the angles can change, but the magnitude of that vector stays the same. So the speed will stay the same, but the reason it's a velocity vector is because that angle is always changing of that object. All right, so this would be an example of we have some object that's in uniform speed going around a circle, and we say the velocity is at a tangent to the circle. Okay, that is a trigonometry term. We will not use trigonometry in this course, so we won't go into it too much. And so you can see the velocity vector is going tangent to the circle. And then you might be wondering, what is that vector that's pointing towards the middle? Well, the acceleration and the force are always directed towards the center in an object in circular motion. Now, if you think about it, think about if you have a ball on a string and you're twirling the ball over your head, right? And let's just say you release the ball, what way is the ball going to fly off? Well, the ball's going to fly off in this straight vector right here, tangent to the circle, okay? So it will fly off in a straight line because there's no more force causing it to go around this circle, right? You were the force causing it to go in a circle, and as soon as that force is eliminated, the object will take off in a straight line tangent to the circle. All right, excellent. Let's start some problems here. Go ahead and take a minute to write these problems down, and we'll do them together. Okay, so let's tackle number 1. So let's go ahead and write down our variables first. So we have a mass of 900 kilograms. We have a radius of 25 meters. And then they want us to find, oh, let's not forget velocity. I apologize. Our velocity is 10 meters per second. All right, so they want us to find acceleration. We don't know what that is. And then they want us to find the force. All right, so we don't know the period in this problem, but we're not going to need it. So let's go ahead and look at acceleration first. So the first one, acceleration equals velocity squared over r. So I'm going to say 10 squared over 25, which is 100 divided by 25. So that's 4 meters per second squared. Okay, so that's my acceleration. All right, well, so then I can go ahead and derive my force from that. Once I know my acceleration, I know that force is simply just mass times acceleration. So force equals mass times acceleration. And again, we'll get into that a little bit more, but I just want to introduce it to you here. So my mass is 900 kilograms, and my acceleration is 4 meters per second squared. So when I go ahead and multiply those, I get 3,600 newtons. Okay, so that's my force, 3,600 newtons. Now let's look at problem number 2. Okay, problem number 2, let's go ahead and pick out our variables. We have a mass of 95 kilograms. We have a radius of 12 meters. And our period this time is 2.1 seconds. All right. So the first thing they want to know is our velocity, acceleration, and then force. So we have all three to find this time. So let's go ahead and do our velocity. We know our velocity formula is 2 pi r over t. So that's going to be 2 times pi times 12 all over 2.1 seconds. All right, so when I multiply that, I get 75.4 on the top. I have 2.1 on the bottom, and I get 36 meters per second, or 35.9, but I went ahead and rounded it up. It should be 35.9 because we have a decimal, one decimal place here, so we should keep one decimal place. So approximately 36 meters per second, or 35.9 meters per second, is our velocity. So our acceleration is velocity squared over r. So that's going to be 35.9. Again, that's from here. This was 35.9 over 12. And square the 35.9. So v squared over r is 35.9 squared over 12. And when I do that, I get 107 meters per second squared. Okay, so what is my force? My force is just mass times acceleration. So that is 95 times 107. And that's going to give me approximately 10165 newtons. Okay, so that's my force. So we can also verify this force with our force formula, which is 4 pi squared r over t squared times m. Okay, so these are the same formulas, same force formula. So we're going to go ahead and type in our calculator 4 pi squared times 12 over 2.1 2.9 squared. Oh, 2.1, I'm sorry, 2.1 squared. So our period is 2.1. So when we type that into our equation, just this part for acceleration, I get 107 meters per second squared. So I again take that 107 times 95 and I get the same answer, 101.65 newtons. All right, so we can see that this formula is the same thing as this formula, right? Even though that object is in circular motion. Let's move on to the next problem now. All right, let's look at one more problem. Go ahead and write this problem down so we can identify our variables and work it out together. All right, so this time we have a child who's on some cliffhanger ride, I'm guessing is what that is, and it's going around the ride. So let's go ahead and see what our variables are. This is problem number 3, and we have a mass of 40 kilograms. We have a he's going to make 10 revolutions in 29.3 seconds. So because this child is making 10 revolutions in 29.3 seconds, that 29.3 seconds is not our t. It's not our period. So our period is actually going to be 10 divided by 29.3. And that's going to give me 0.34 seconds. Okay, so 0.34 seconds. That's actually our t. And then our radius is 2.9 meters. And this problem is just asking for the force. So we can go ahead, we cannot use F equals ma because we don't know what A is, right? So we're going to have to use our formula for 4 pi squared r over t squared times m. So let's go ahead and put that in our calculators. We have 4 pi squared times 2.9 over 0.34 squared times 40. All right, so let's go ahead and figure out what is the acceleration. Okay, so when I multiplied my top numbers, I got 114, and then I divided that by 0.12, which is what 0.34 squared is. And so my acceleration came out to be 950 meters per second squared, and then times 40, which gives me approximately 38,000 newtons. Okay, so that's what I got for my answer, 38,000 newtons. See what you got. Now, your answer may be a little different. If you didn't round off in your calculator, you might have got like 38,100 if you didn't round off this 114, and that's perfectly fine. It's close enough. The 100 is not significant compared to the 38,000. I know that probably sounds like a lot of force, 38,000 newtons, but just to let you know that it takes approximately 1 newton of force to beat your heart for 1 heartbeat. So although 38,000 sounds like a lot of newtons, it's not really when you think about 1 newton is a heartbeat. So you can see where, you know, any object would require a lot more than just 38,000. I mean, then, you know, it's not that big of a number, right? So, okay, well, that will take care of circular objects in circular motion. And so you'll learn about satellites a little more, and we'll talk about those kind of problems in some other videos that are in this section of the module. And so we'll see you next module.